Hello everyone and welcome to Module 6. In Module 6 we'll talk about one-way ANOVAs and the post-hoc testing that comes along with those. So we'll talk a bit about the basic logic of ANOVAs, and I'll say this in a few different ways. This is pretty similar to the t-test, but the ANOVA can be used to test can be used in situations where we're interested in the differences in sample means across 3 or more categories of an independent variable. So if you remember when we looked at t-tests and we did an example, we looked at gender differences, so comparing males to female, so that's an independent variable on which we have 2 groups, 2 categories. And so the ANOVA is a situation in which we want to ask a similar kind of question about group differences, but we have an independent variable where we have more than 2 categories, so 3 or more categories of that independent variable. And so you might ask, and your book covers this a little bit, why don't we just conduct multiple t-tests? And the basic answer to this is that conducting multiple t-tests carries with it the possibility of inflating our the potential for type 1 errors. So essentially, the more t-tests that we run, the greater the risk that we'll reject the null hypothesis when it's actually true. So inflating the potential for a type 1 error. So the ANOVA allows us to conduct multiple group comparisons without inflating that error, that type 1 error. So the ANOVA asks, are the differences between the sample means so large that we can conclude that the populations represented by the samples are different? So again, if you remember from the t-test, we talked about wanting to understand group differences in different populations, whether those are men or women or various other populations we might be interested in. And in order to test that question, to answer that question, we collect samples from those populations. And so following that same logic, the ANOVA asks if the differences between the sample means are so large that we can conclude that the populations or the groups in the world are actually different. So the null hypothesis is that the population means are the same. So again, the means across whatever groups, and this K represents the number of groups that we have. So the group mean of group 1, 2, 3, etc. are all the same. And so the population means is what the nomenclature there is. And so if the null hypothesis is true, the sample means should be roughly the same value. If the null hypothesis is false, there should be substantial differences between the categories, combined with relatively little difference within the categories. And so I'll say a little bit more about this between versus within distinction, because this is really a key piece of the ANOVA. So ANOVAs are based upon the idea that the total variance can be divided into 2 parts. We have within group variability and between group variability. And so within group variability is the amount of scatter that we have within the subgroups. So if you think about within groups of, let's say, let's just talk about 2 groups still. If we're talking about males and females, the variability that we have within the group of males and within the group of females, that's the within group variability. And then the variability between groups is the amount of scatter that we have between the subgroup means. So looking between men and women, how is that variability distributed? And so the ANOVAs basically try to understand if the between group variability is essentially bigger than the within group variability. So we know that there is always variability. Men are going to score differently on a certain outcome. Women are going to score differently from one another on a certain outcome. And so we want to know if the differences between the ways in which women score and which men score are greater than the differences within each of those groups. And so the larger the difference between the sample means, the more likely the null hypothesis is false, especially when there is very little difference within the categories, or a smaller amount of difference within the categories. So when we reject the null hypothesis, in this case, we're saying that there are differences between the populations represented by the sample that we have. And so with an ANOVA, though, we don't understand or we don't know where those differences are using just the basic omnibus ANOVA, or omnibus F test as it's often called. We don't know where those differences are, so we have to conduct post hoc comparisons to determine the location of those differences, so which groups are different from one another. And I'll say more on that in just a second. So I'm not going to say much about this. We talked about distributions when we talked about the normal distribution. I introduced the t distribution, which is a variation on that, but depends on degrees of freedom. And the same thing is true here. F is another kind of probability distribution. It's kind of like the standard normal distribution or a t distribution. It's a non-symmetrical distribution, unlike those other distributions. And like the t distribution, its shape depends on the degrees of freedom involved. So this is another situation in which we're going to be looking at degrees of freedom and thinking about how those impact the decisions we make about this statistical test and whether or not to reject or accept the null hypothesis. So as we think about what kinds of questions are appropriate for ANOVAs, your book obviously has the chart, and there are various other charts available online as to which kinds of tests you use in which situations. The kinds of questions that we ask that are appropriate for testing via an ANOVA are things like, how do Republicans, Democrats, and independents vary in terms of attitudes about the morality of abortion? So this would be a situation in which we would be looking at mean differences, so the mean on this dependent variable, attitudes about abortion. And the independent variable here is political affiliation, and we have 3 levels: Republicans, Democrats, and attitudes. And so we would be looking at group means, so the mean of attitudes for Republicans, the mean of attitude for Democrats, and the mean of attitudes for independents, and looking to see whether those are significantly different from one another. Another question that we might ask would be, how do younger adolescents, teenagers, and young adults vary in terms of their perceptions of parental attitudes about their sexual activity? So there's some variables, some questions that ask this in the AdHealth data set. So we could potentially take the continuous variable of age and break it up into 3 groups. So this is a situation in which we actually, our independent variable of age is originally a continuous variable, but we could actually take that variable and make it categorical and turn it into a 3-category independent variable. Younger adolescents, we could decide what we wanted to break that up, maybe like 12 to 13-year-olds or something, 14 to 18-year-olds. We could think about how we wanted to break that up, and young adults, so those who are over 18. And how do they vary in terms of their perceptions of parental attitudes about sexual activity? So this would be our dependent variable that we're looking at. And that's also a continuous variable. Another question we might ask that would be appropriate for ANOVA testing would be, how do different racial and ethnic groups vary in their contraceptive self-efficacy? So this is coming back to the example that we discussed in the t-test module, using that scale that we spent some time on in Module 5. And again, this would be a situation in which racial and ethnic groups would be categories. So this is a categorical independent variable. And I'll talk more about how we might split that out towards the end of the lecture. And then contraceptive self-efficacy is a continuous variable. This would be our dependent variable. We're trying to predict scores on contraceptive self-efficacy using the independent or predictor variable of race and ethnicity. So these questions would all be appropriate for ANOVA. And so some assumptions of the ANOVA test, much like the t-test, an assumption is that these groups are independent. So the groups that we're looking at is independent variables. The categories are independent from one another. So male and female don't overlap. Democrat and Republican, in strict affiliation, don't overlap at all. Another assumption is that we have a continuous outcome variable, continuous dependent variable. So interval or ratio data on that dependent variable, and that people are normally distributed on the dependent variable. And so we'll talk more about violations of that assumption in just a second. And then, much like the t-test, we also have an assumption that there's homogeneity of variance and or equally sized groups. So the homogeneity of variance assumption is fairly robust to violation, particularly when we have equally sized groups on each of those categories. So let's talk a little bit about conducting and interpreting ANOVAs. The Cronk textbook with the sort of step-by-step how-to for SPSS will give you an example of actually how to conduct that. But let's talk through this 4-step process. And again, as we talked, a lot of people use a 7-step or an 8-step process. We're cutting out some of the steps for demonstration purposes here. So we'll talk about this 4-step process of stating the null and alternative hypotheses, making sure you meet the test assumptions, calculating the test statistic, and making a decision and interpreting the results. So in step 1, in a situation where we would have an ANOVA, we would want to state the null and alternative hypotheses. And as we talked about before, the null hypothesis would say that the population means are the same. So group 1's mean, group 2 mean, group 3, and so on. We could have as many groups as we needed here, but we could talk about how many would be useful in terms of interpretation, that these population means are the same. The alternative hypothesis states that at least one population mean is different. So at least one of these things is not like the other, basically. And so if we reject the null hypothesis, the test doesn't actually specify which population mean is different from the others. So we'll talk about conducting post-hoc tests in just a second. So again, we'll make sure the assumptions are met and that we've met the test requirements. So again, that our groups are independent, that our categories on whatever categorical independent variable we're using are independent, that the level of measurement of the dependent variable is interval or ratio, essentially that it's a continuous variable. And the dependent variable for both t-tests and ANOVAs, the dependent variable should be continuous so that we can justify using the mean as our metric of that variable. So if we're looking at a variable where the mean is not appropriate, where it'd be more appropriate to look at the median or the variance or some other description of that variable, then using a test that does a mean comparison wouldn't be appropriate. We want to make sure that populations are normally distributed on the dependent variable, and again, with large samples, this test is fairly robust to to a violation of this assumption. And we want to make sure that our population variances are fairly equal and or that our group sizes are roughly equal. And then we'll calculate the test statistics. So your book walks you through very step-by-step how to calculate this and the sum of squares. And I think it's useful to think through that formula and how we get to this statistic. I'm not going to go into it a ton here, other than to say that lucky for us, we can use SPSS for this. So you can look at your text and maybe play along with one of the examples given in your text of how to calculate those. I think it's really useful to see that process, but your book does a really nice job of that, and so I'm not going to go into a ton of detail here on that. And then again, in step 4, we'll make a decision about whether or not we reject the null hypothesis or fail to reject the null hypothesis. And so when we fail to reject the null hypothesis, again, this is the space here in a distribution. This is the normal distribution for description purposes only. If we fail to reject the null hypothesis and conclude that there is no statistically significant differences between population means on the dependent variable, or we can reject the null hypothesis and conclude that there is a statistically significant difference between groups on the dependent variable, though we actually don't know, again, which groups differ from one another via that omnibus F test. So the way that we find out where those group differences are is via post-hoc testing. And your book does a nice little description of this, but we'll talk a bit more about this in the lecture. When the omnibus F test is significant, we conduct follow-up testing to determine where that difference lies. And we conduct typically pairwise comparisons to show where a difference lies. And pairwise comparisons means that we compare every pair of means. So if there are 5 different groups, then we're doing each of those means compared to each of the other means. Typically we do less conservative, we have sort of options in terms of what kinds of post-hoc testing we want to conduct. So we may do less conservative tests to increase the, less conservative tests will increase the risk of type 1 error. So LSD pairwise comparisons, the more conservative tests will increase the risk of type 2 error. So we're often trying to balance and use a test that is somewhere in between. We may make decisions based on the sample that we have or based on the kinds of questions that we're asking but these more conservative tests will increase the risk of type 2 error. So Bonferroni's, which tends to be better with smaller number of comparisons, or Tukey's, which tends to be better with a larger number of comparisons. And we'll also show an example of the Gabriel's pairwise test. And so that would be useful in a situation in which we have unequal group sizes or unequal group variance, which does happen. So this is sort of a way around that, making it so that the entire ANOVA is not sort of null and void. And I think your book gives some examples of other kinds of ANOVAs that you can use if some of these violations are, if some of these assumptions are violated. We won't talk a ton about those here though. And so when we interpret the results, as always, we'll look at the value of the alpha. The higher the alpha, the more likely we are to reject the null hypothesis. We look at the size of the sample. The larger the sample, the more likely we are to get a bigger alpha and then to reject the null hypothesis. And we'll report all comparisons that are significant, trying to look for patterns in those. And I'll show you an example of that in a moment. And we also need, again, to look at the means to determine how to report the data and to think about what the clinical or practical significance of statistically significant mean differences actually is. So same kind of idea in terms of the interpretation as we talked about with the t-test. This is just a situation in which we have more than two groups. So as I mentioned before, the F-test also has degrees of freedom associated with it. This F-test, again, is essentially a fraction. If you follow along in your book, you can see that formula and how that eventually breaks down. And so the fraction obviously has a numerator and a denominator. And the F-test then has two sources of degrees of freedom. So in the numerator, the degrees of freedom come from the number of groups, and we do the number of groups minus 1. And in the denominator, the degrees of freedom is the number of observations, the number, so the size of the sample, minus the number of groups. And when we report an F statistic, we always report both of those degrees of freedom. And I'll show you how to do that using the output in just a moment. So we report, this is sort of how the APA format of this looks. So F, the numerator degrees of freedom, the denominator degrees of freedom, your F value, and then your P value here. So let's do a full example and really think about how to apply what we know about the ANOVA. So again, step one, let's lay out a research question and some hypotheses. We'll stick with this contraceptive self-efficacy outcome variable that we used in the Module 5 t-test example. And we'll look at a different independent variable here. So we looked before at biological sex, looking at male versus female. And in this situation, let's look at race and ethnicity. So do racial and ethnic groups vary in their levels of contraceptive self-efficacy? And so our null hypothesis is that all of these groups are different. In this situation, I'll show you a race and ethnicity variable that has 5 different categories. So in this situation, we're saying that all 5 of these groups are the same. There's no difference in population means on contraceptive self-efficacy according to racial and ethnic group. And the alternative hypothesis is that at least one group mean is different from at least one other group mean. So I'll walk you through this example. For those of you who are interested in race and ethnicity for your final paper, for your brief report question, I've uploaded a new data set that actually has the race and ethnicity variable in there. Because this is wave 2 data, the race and ethnicity variable wasn't included in there. That's a question that if you ask somebody the first time on the survey, theoretically that shouldn't change between the first survey and the next time. So that variable wasn't in the wave 2 data, so I've gone back and uploaded that into the wave 2 data. And so now you can see that. The problem with AdHealth is that they did some fairly complex ways of asking about race and ethnicity. And so they didn't have a complete variable in there. So I spent some time crunching the data and creating some syntax that creates a variable that is not perfect in terms of the way that it categorizes race and ethnicity, but it helps to give us somewhat equal groups. And I'll show you how those groups look in just a moment, and you'll understand what I say when I mean that they're not perfect. So once we have our research question and our hypotheses, so do racial and ethnic groups vary in their levels of contraceptive self-efficacy? Our null hypothesis is that populations don't vary. Alternative hypothesis is at least one group mean is different from the others. And the Huck text actually talks about the distinction between planned comparisons versus post hoc tests. This is a situation in which we're not setting out with any particular hypothesis about which groups might be different from one another and in which directions they might differ. We're saying we think race and ethnicity may have something to do with group differences in contraceptive self-efficacy, but we're not laying out any planned comparisons. So we'll use post hoc tests to understand the ways in which there might be differences and figure out where those differences are. So next we'll check that our assumptions are met and that we can actually use the ANOVA to answer our question. So again, are our observations independent? Are our groups independent from one another? Yes, these are. Our level of measurement is good for both the dependent variable being continuous and the categorical independent variable. We'll check that there is equivalence in size and variance of groups. The groups range a bit in size for this example. We'll check the equality of variance in the analysis, and that's under the options button when you go through to do the ANOVA. So at the same place where you check descriptives under options, just a couple of boxes down from there is check the variance of groups. And so we'll talk a little bit more about situations in which this might be violated, but these groups definitely are different in size in this situation. And so much like we did with the t-test, we'll check the distribution of contraceptive self-efficacy and look to see if that variable is normally distributed. And as we talked about in the t-test module, the answer is meh. There are some issues with this variable, but because this is a very large sample, we won't worry as much about it. So we'll move forward with this particular example. And so we'll conduct the test in step 3, and this is the syntax that we use for this. And so in this situation, I conducted a Bonferroni. Once I realized that the variances were unequal, I went back and changed that to a Gabriel. And so I'll show you an example of the Gabriel post hocs in just a couple of slides. And so as we see here, we tested the homogeneity of variances, and what we found is that there are significant differences in our variances across the groups. And so I'll talk about correcting for that. So this is a situation in which we can correct for that in post hoc tests. And again, because we have such a large sample, we're going to worry about it less, although it may be a little bit of an issue because our group sizes are fairly different from one another. So this is a situation in which maybe it's not the most ideal situation. We might want to think about using a different kind of ANOVA, but for the purposes of description and demonstration right now, we'll go ahead and stick with what we have. I feel like your parent saying, do as I say and not as I do. So what do we do? What do we see when we get our ANOVA? So aside from testing for the equality of variances, we get our descriptive box up here. This is the box that you're checking for in options that you want to make sure that you get, because this gives you all the group means. It gives you the N. So as we see here, perhaps not surprisingly on most surveys, we see that there are more white folks than any other group. And then we have a fairly large sample of Black and African Americans in this group. Latino is our next largest group, and then folks who are multiracial down here. And then Asian Pacific Islanders, and then this group, this is one that I crunched some folks together. So this is American Indian Native Americans. There were, I believe, 55-ish of those folks, and then adolescents and young adults who checked other. So these people are all pushed together here into a fairly small group. What a lot of people do in analyses is actually just get rid of everybody who is not in that large of a group, or sometimes lump them all together into another group. So in this situation, I could see somebody saying, all right, we're going to keep whites, Blacks and African Americans, and Latinos in this group. But maybe everybody else, we're actually just going to kick them out of the analyses altogether, or push them together into groups because we don't have enough of them to be able to make useful comparisons. And once we start getting into so many groups with such small n's in each of them, we do run into some issues violating the assumptions of the ANOVA. So what we see here is the group size, the mean and standard deviation and standard error, these 95% confidence intervals, which I believe your book talks about a little bit, but we won't spend much time with here, and then the minimum and the maximum. And this is what the scale minimum and maximum are for most of these, is 3 to 15. And then down here we have the actual ANOVA. And so contraceptive self-efficacy is our outcome here, and we have the sum of squares, the between groups, and the within group sum of squares, and this is the total. This is these two added together. We see our degrees of freedom here. So this one is 5, and then 37.13 here, and our mean squares here, and then this is our actual F statistic. So 12.259 is the number that we'll report. We'll round that to 12.26. And this is our p-value. So again, this one is one that we'll report as p is less than 0.001. And so what we know here then is p is less than 0.05. So if we wanted to present these ANOVA results in a table, this is a possibility for what a table could look like. Often people are presenting more than one independent variable in the situation. So race, ethnicity, then under here gender, then maybe relationship status, etc. So these are the different categories that we have: white, black, Latino, Asian Pacific Islander, this other Native American, American Indian group, and multiracial. So we have 6 categories here. And these are the means and standard deviations for each of them. And then this is this F statistic. And this should actually have 3 stars behind it here. I just left those off accidentally. And so some people don't do this little P sort of a thing under their tables. Some people will actually put the p-values in here. It's up to you how you lay out your tables to some degree. And so again, as I mentioned, what we know from this F test is essentially just that our omnibus F is significant. So somewhere in here, there are some differences. One of these means is not like the others, essentially. And so we actually have to run some post-hoc comparisons to figure out where those differences are. So as I mentioned, I did the Gabriel post-hoc comparisons here because we did have inequality in our group variances. And so what we're looking at now, we have over here each of our racial and ethnic categories, and then here we have them again. And so what we see here is that this box right here, this is people who are white compared to each of the other groups. So whites compared to blacks, African Americans, whites compared to Asian Pacific Islanders, etc. And then we have the mean difference. These are the means subtracted from one another. So we see the size of that difference here. These stars indicate significance. And if we look over here to the p-value, we see what that p-value actually is. And so in this situation, we're actually looking at these and trying to figure out where these differences are. And so we'll see them in multiple places. So if we look at here, whites versus Asian Pacific Islanders and whites versus Latinos. So there are significant differences there. If we look at blacks and African Americans, there's a difference again between Asian Pacific Islanders and Latinos. So not surprisingly, when we go down here to Asian Pacific Islanders, there are several group differences. So they are significantly different from whites, blacks and African Americans, this other sort of amalgam group that I have here, and folks who identify as multiracial. And then this sort of catch-all group here is significantly different, obviously, from Asian Pacific Islanders. And then if we go down here to the Latino group, we see differences here between Latinos and whites, which we already saw up here, blacks and African Americans, which we already saw up here again, and then again multiracial down here with Asian Pacific Islanders, which again we already saw. So as we report these and think about making sense of these differences, it's useful to think about where, which group has the most differences compared to other groups. And that really seems to be Asian Pacific Islanders. And so we can look and see they are different from most of the other groups with the exception of Latinos. And if we look down here at Latinos, Latinos are significantly different from both whites and blacks and African Americans. And so we can go back to these means here, which are both here in this output and here, and we can look and see what we're looking at in terms of these differences. So go to Asian and Pacific Islanders, their mean score is 6.4. And they were different from most other groups, which we can see that they're higher than most other groups. And then if we go here to Latinos, we can also see that they are higher than most of the other groups, and they were different from whites and blacks. And so when we report this and make our decision and interpret our results, so again, we report our F here and our degrees of freedom. These are our two different degrees of freedom here. Our F value, our P value. We know obviously that we're rejecting our null hypothesis in this situation because P is less than 0.05. All right, this is a big mouthful, but I wanted to put all of this in here to give you a sense of how to report it. Your Salkind book doesn't give many examples of the language to report it. The Cronk book does give a couple of examples of how to say and how to report in text the basic ANOVA test and some of these planned or post hoc comparisons. And actually, though, I'm going to say go ahead and skip the Huck reading. If you want to look in the Huck chapters in those little gray boxes, they actually do give examples from articles of how to say some of these things. So that might be a useful piece of that chapter. So what we can say here are that contraceptive self-efficacy scores range from 3 to 15. This is exactly what we said when we talked about the t-test last time. Higher scores indicating lower levels of self-efficacy. So again, we have to think about sort of flipping that around here. And so a one-way between groups ANOVA indicated that there were significant differences in contraceptive self-efficacy among racial and ethnic groups. We could put our total F here if we wanted to. And then we did post hoc Gabriel's tests used to account for unequal group variance, indicated several pairwise group differences. As a group, Asians and Pacific Islanders scored higher on contraceptive self-efficacy than adolescents and young adults who identified as white, black or African American, American Indian, Native American or other, and multiracial. Latinos scored significantly higher on contraceptive self-efficacy than those identifying as white or black African American, and these are all those means respectively, which when we interpret this, we have to then flip that again because we have to remember that higher scores indicate lower levels of self-efficacy. So in fact, when we're looking at this, Asians and Pacific Islanders and Latinos actually had less self-efficacy as a construct than the other groups. And our largest group difference on this scale is 1.49 points on a scale ranging from 3 to 15. So again, we have to think a little bit about, is that important? Is that a difference that is meaningful to us when we're thinking about contraceptive self-efficacy overall? And we see where this group difference is, this 1.49 is, if we go back and look here. So for Asian and Pacific Islanders compared to the other groups, this is the mean difference here. So this 1.49 is the largest difference that we see here if we're looking at all the mean differences here. So those are the basics for the one-way ANOVA. In Module 7, we'll extend this and make it a bit more complicated, talking about factorial ANOVAs, where you can actually look at two different independent variables, both on their own and in combination with one another. For the Module 6 assignment, you'll be conducting a one-way ANOVA. You'll download the data set and answer the research question proposed in the assignment, though there is only one test that you could possibly conduct to answer this question in this example. I still want you to give me a sense of that you used an ANOVA because the ANOVA is appropriate for this question because of the independent variable that you have. So to give me some justification for why the ANOVA is appropriate. You'll write up a results paragraph. Again, for this one, don't worry about making a table. Again, APA format, please, 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 APA format. And so the Module 6 assignment is posted there and it's linked in the course content here. And as always, let me know if you have questions or thoughts, email me or post those under the general discussion forum.